Hello everyone and welcome to a new problem in applied math for architecture. In this problem, we are told that we are designing some sort of auditorium, and the auditorium has two ceilings, the main ceiling, a plane, and a secondary ceiling, gamma, first plane pi. And then there is a support beam, a line that intersects plane gamma, the secondary ceiling, and we must find the distance from point P, intersection of the support beam with the secondary ceiling. Remember that the intersection of a plane with respect to a line is a point, therefore the distance from that point, that intersection point, with respect to the main ceiling. So as usual, we can make a sketch, even though it's not very accurate, but just to have a rough idea of what's happening. So let's say that this is plane pi, for instance, right? Plane pi, the main ceiling, and then at a different position or whatever, we have plane gamma, secondary ceiling. Again, I'm aware that these two planes, they probably do not represent the numbers given in the problem, but it's just a sketch. And then the support beam, described by a line. So this is the support beam. And intersects. Okay. So here we have the intersection point. Let's use purple. And we want to find the distance from that intersection point, to main ceiling pi. That's the goal of the problem, this distance. Okay. So let's define objects first. Regarding main ceiling pi, contains 3 points. So contains A, B, and C. We need a point and two vectors in order to create a plane. So for the point, all three are equally good. Let's take B, just because it includes a 0, nothing else. 0, 1, 5. And two vectors, given 3 points, it's always possible to create vectors connecting the dots, connecting the points in any direction. Any combination is valid. So for instance, vector AB and vector AC. Endpoint minus starting point, B minus A, would be -2, 1 and 2, and AC endpoint minus starting point, -1, 3, and 1. Okay, -1, 3, and 1, correct. So this 3 by 3 determinant, x minus the point, y minus the selected point, z minus the point, and then the two vectors, -2, 1, 2, -1, 3, 1. Main diagonal, x, here this triangle, here opposite corner, -6 times z minus 5, this opposite corner, -2 times y minus 1, secondary diagonal with opposite sign, so plus z minus 5, this opposite corner with opposite sign, -6x, and this opposite corner with opposite sign, plus 2 times y minus 1. Simplify, 2 times y minus 1 minus 2 times y minus 1, they cancel out. And we obtain, concerning x minus 6x, -5x, and then it's minus 6 times brackets plus 1 bracket, it's minus 5 times the brackets. Okay, so it's minus 5x minus 5z plus 25. This is plain pi. Good. Now we need point P, intersection of gamma and R. This is line R. Let's do it next slide. So how do we find the intersection of a line and a plane? Well, solving the system of equations that describes both objects. And it's always the same idea for any two objects. So the intersection of two mathematical objects is the solution of the system they create. So line R, I'm going to use, just for convenience, the parametric equation. So point plus vector. If line R has direction D, this vector D is R, is the direction vector of line R. So it's for the x component 1 plus t, for the y component negative 1 plus 2t, negative 1 plus 2t, and concerning z would be 2 minus 1t. So 2 minus t, and we claim that t extends for all real numbers, right? And plane gamma was given by equation 2x minus y plus 3z equals 6. 2x minus y plus 3z equals 6. So if we substitute the line inside the plane, all of a sudden we reach an equation with just one unknown, which is t. So substitute. Instead of x, 1 plus t, then minus y, which is minus 1 plus 2t, plus 3 times z, which is 2 minus t, equals 6. Clean it up, expand and fold. 2 plus 2t plus 1 minus 2t plus 6 minus 3t equals 6. Simplify. 6 on the left, 6 on the right, they cancel out. Plus 2t minus 2t. So we end up having that 3 on the left equals 3t on the right, and therefore t equals 1. So the intersection, the entire line is described for all values of t, but the intersection is produced exactly at t equals 1. Hence, P has coordinates x, 1 plus 1, right? Remember, when t equals 1, coordinate y of the intersection point, minus 1 plus 2 times 1, and z 2 minus 1. So point P coordinates 2, negative 1 plus 2, 1, 2 minus 1, 1. Finally, according to the formula of distance between points and planes, the distance from point P to plane pi, since pi was given by the equation minus 5x minus 5z plus 25, minus 5x minus 5z plus 25, right? Which looks like coefficient times x plus coefficient times y plus coefficient times z plus d equals 0. The equation was upstairs, absolute value of a times px plus b times py plus c times pz plus d, and downstairs the modulus of the normal vector, namely square root of a squared plus b squared plus c squared. So more specifically, in this case, it would be minus 5 times 2, right? Coefficient of the plane times coordinate, then plus 0, y 0, since b, for this plane, b equals 0, there's no y, plus c times p set, so minus 5 times 1 plus 25, divided by square root of a squared, a equals negative 5 squared, plus b squared, which is 0, plus c squared minus 5 squared. So upstairs, negative 10 minus 5, negative 15 plus 25, 10. Absolute value of 10, just 10. Divided square root of negative 5 squared, 25, and again another 25. So it's 10 over root 50, and this is good enough. Maybe we can clean it up a little bit. It's 10 times root 50 divided by 50. So using rationalization techniques, and therefore it's root 50 over 5 units of length. Root 50 over 5 units of length. And that's it. Thank you very much. See you in another problem. Bye.